Okay, next up is University of Michigan Dearborn, Hashim Ali. Good.
Hello everyone. Can you guys hear me? Um, Mic working? Yeah. Yeah, I want to close. Okay. Hello everyone. My name is Hashim Ali, and I'm a PhD candidate at the University of Michigan Dearborn. Today I'll be talking about our submission for the SAFE challenge, which is titled as Multilingual Dataset Integration Strategies for Robust Audio Deepfake Detection. Our team name is ISSF, and our team members include Surya Subramani, Nitin Arupa, Lekha Balinani, Sali Ello, and our esteemed advisor Hafiz Malik. So before we dive deeper into what we did for the SAFE challenge submission, here is a brief overview of what we achieved in this challenge. We achieved a balanced accuracy of 0.81 on task 1, and 0.82 on task 2, and 0.623 on task 3. So these balanced accuracies are actually on the public dataset. So I realized after Krill's presentation that we were supposed to look at the private letterboard. And on the public letterboard, we got second rank, and on the private letterboard, we got third rank. So let's discuss briefly what is Safe Challenge and why it matters. We know that audio deepfakes are increasingly getting more sophisticated. A few examples include the Biden robocall incident in New Hampshire, and there is another example of Mayor of London Sadiq Khan targeted on Armistice Day, and there are like many more examples of deepfake incidents these days. So why this safe challenge is unique is it is totally fully blind evaluations, and it contains very realistic three threat scenarios. And the data that it provides is very balanced between the synthetic and the real audio samples. So previous challenges, it is very imbalanced. For example, ASP spoof, you would get like a lot of synthetic samples and very few real samples. But this challenge, the focus is on the balanced number of samples. So the goal of this challenge is to build a robust detector that generalizes to unseen attacks and languages, while in the presence of processings and laundering attacks. So the three threat scenarios is I'll very briefly go over it. Task one is unmodified or synthetic audio detection. Task two is there is some processing, audio compression, resampling, etc. Task three is laundering attacks, adversarial processing. So when we were developing the model for this challenge, we thought that the data is not provided to us. What can we do about this challenge, and how can we train our model? So we were not provided the data set, but we were provided some description of the data set. That description include that human speech is sourced from multiple sources, and it is multilingual, and the human speech is also very high quality and in studio recordings, and very low quality in the world recordings as well. And machine generated speech consists of state of the art TTS systems, and it will be generated through open source and commercially available tools as well. And we know that the maximum audio length in the dataset, saved dataset, is 60 seconds, but it varies. And again, it's a very balanced data set, balanced across sources. So is there one single data set that's enough that can capture most aspects of this safe challenge? So after doing a brief overview of the available datasets, we found out that most datasets have specific coverage. For example, ASP Spoof 19 consists of traditional neural TTS systems, which, for example, WaveNet, Decatron, etc., and it's only English and it's only clean conditions. Similarly, some other datasets provides codec-based TTS systems, and they lack the latest technologies. Similarly, some datasets would provide lab conditions, and some datasets would provide like real-world data. So we need a data set that covers most aspects of the safe challenge. So then the question is, what data sets should we combine that provides us the maximum coverage for unknown attack generalization? So we did a data set coverage analysis, and we looked at multiple data sets. And these are only a few data sets that we have mentioned here, but we also looked at other data sets. And we found out that, for example, codec fake contains 15 codec audio models. ASP spoof contains 19 TTS systems. MLAT contains 54 to 91 TTS systems. Spoof self consists of 23 contemporary systems, and famous figures, which we created ourselves, consist of only 10 TTS systems. And each data uses specific TTS architecture. For example, codec fake uses speech tokenizer, academic codec, etc. MLAT uses BITS variants, speech T5, etc. Our famous figures data set consist of style TTS2, XTTS V2, etc. And again, the focus is complementary focus. Codec fake provides neural audio codec. ASP spoof 19 provides a traditional and neural mix. MLAT provides language diversity, and spoof celeb would provide more real world conditions. And famous figures focuses on real world and the latest TTS systems. So we structure our analysis based on around 3 factors. The first factor is the TTS systems, whether the TTS system is used is traditional, latest, or totally different, as in the case of neural audio codec. And then what acoustic conditions that data provides. For example, does it contain clean lab recordings or book readings, etc., or real world noisy conditions? And the third is what languages and how many languages it provides. For example, ASP spoof 19, spoof celeb, codec fake, famous figures, they're all English data sets, and whereas MLAD and MIA labs, they are multilingual. So we got 3 key insights from this coverage analysis. We saw that most datasets focus on specific paradigms, and we need optimal complementarity between among datasets. We want to combine codec-based system, codec-based audio samples, multilingual audio samples, real-world audio samples, and cutting-edge latest CTS systems. And we also need all types of acoustic conditions in our trained dataset, which ranges from clean studio to audiobook to real-world robustness. After figuring out what dataset we need to train the model on, we performed a brief SSL feature selection analysis. We generated UMAP embeddings for various SSL embeddings, and we tried to only using the ASP spoof 19 dataset, and we tried to see which one gives us better separation among the between the real and the fake. And after doing this analysis, we found out that WavLM Large and MAST performs much better than the other SSL features. So this is our model architecture. We resample all the audio samples to 16 kilohertz. We either use 4-second or 12-second padding for the audio samples, and we also use raw boost data augmentation. So after that, after the pre-processing step, the audio will go towards the feature extraction, where we either compute the WavLM Large SSL feature or the MAST frame SSL feature, and then the output will go to the AASIST backend, and then that will do the classification for us. So we submitted the models to the safe challenge in 4 iterations. So our iteration 1, we didn't do anything. We just got the ASIS model, trained that model on the ASP spoof 19 dataset, right, which is very traditional, and that's our iteration 1, and that will also make our baseline submission that we can compare the model for other iterations. And this database, ASP Spoof 19 database, contains 25K samples. So iteration 2, we trained the model on multiple datasets. We used 25K samples from ASP Spoof dataset, and then we sampled 20K samples from MAI labs, spanning 8 languages, which are English, French, German, Italian, Polish, Russian, Spanish, and Ukrainian. And after that, we sampled around 47K samples from MLAD dataset, but only focusing on the languages provided by the MIA labs. And and for each dataset, we did 80-20 rule. We for each dataset we kept 80% of that dataset for training and 20% for the validation. This is our iteration 2. So in our iteration 3, we kept the same dataset as in iteration 2, but we only changed the audio length padding. Now we pad the audio length to 12 seconds. Before that, we only padded to 4 seconds. Right. And then in iteration 4, we added another dataset, which is spoof celeb. We added around 100K samples from spoof celeb dataset, and more changes that we made in this iteration is now we strategically sampled 60K samples focusing on languages present in MAA labs. So this strategically sampling means that we kept certain languages and certain TTS systems unseen in the validation, and kept certain languages and certain TTS systems in the trained dataset. So that gives us more generalization. And we did the same thing for MAA labs, 60K samples from MAA labs. So in total, we got around 200K samples for training, out of which 101K were real and 99K were fake. And we have a validation set of which 56K samples were 29K were real and 27K were fake. So again, the key insights in this in the iteration 4 is we did strategic train validation splits. We did language specific TTS coverage, and we also included unknown languages in the validation set, and we included real world noisy data integration, and we did balanced authentic and synthetic samples. So here's our performance. On task 1, in iteration 1, our traditional ASIST model, which is trained on ASP Spoof 19 dataset, achieved a balanced accuracy of 0.531 on task 1, and 0.589 on task 2, and 0.492 on task 3, which is very not that good. And then in iteration 2, which is multilingual dataset, multiple datasets, our WavLM model achieved a balanced accuracy of 0.745 on task 1, 0.587 on task 2, and 0.478 on task 3. Similarly, our MAST frame model achieved a balanced accuracy of 0.607 on task 1, 0.587 on task 2, and 0.597 on task 3. And in iteration 3, we only used WavLM model. We didn't use MAST frame model. And in iteration 3, it achieved a balanced accuracy of 0.766 on task 1, 0.765 on task 2, and 0.518 on task 3. So last iteration, iteration 4, our WavLM model achieved a balanced accuracy of 0.81 on task 1, 0.819 on task 2, and 0.496 on task 3. And MAST frame model achieved a balanced accuracy of 0.640 on task 1, 0.536 on task 2, and 0.623 on task 3. So all these values are actually for the public leaderboard. I didn't include the values for the private leaderboard, which are different, of course. On top of evaluating the models on the SAFE challenge, we also did evaluation in the wild dataset just to see whether our generalization actually works or not, because in the wild is a very standard dataset used to evaluate the generalization of the detectors. Our iteration 1 has an ER of around 3.35%, and iteration 2 achieved an ER of 8.46% for WavLM model and 25% for MAST frame model. Iteration 3 achieved an ER of 12% for WavLM model, and iteration 4 achieved an ER of 8.42% for WavLM model and around 34% for MAST frame model. So again, these are the challenge results. We got second place on the public leaderboard, private leaderboard we got third place. So this just validates that this approach works to get more generalization and robustness. We need the more diverse data set, which includes various and latest CTA systems, various languages, etc. And sometimes, if you are dealing with unseen scenarios, you would want to cover more breadth rather than more depth to cover every aspect of the data set. So here's the source level analysis. Um, on task 1, our model suffers on G02 and G10. I'm not sure what these generators are. Probably Krill knows. And on task 2, we performed a bit better for on G02 and G10. Task 3, it looks like we are doing really good for task 3, but we are more inclined towards the deepfake or synthetic audio as compared to the real audio because we performed really bad on the pristine audio sources. So so that's it from our side. You can find. So I have mentioned famous figures dataset in the presentation that we have created ourselves, and that dataset just got accepted at InterSpeech. So you can access the dataset from this QR code, and I've also linked our lab, and we also have a web portal where you can upload an audio and we can verify whether the audio is fake or real. Thank you so much.
And then maybe the next presenter can